Good evening, everybody. This is Mr. Steele. I'm back trying to make another video while I'm out with back surgery. In this case, I'm going to be going through the new analysis review that I wrote literally laying in my bed yesterday when I was exhausted. So anyway, I'm hoping this review is pretty comprehensive. I think that it is. I think I've covered basically every type of question with some variety that you might run into in this unit. But at the same time, obviously, I know there's a lot here. So as usual, try to pick out the problems that you're really wanting to spend your time on and focus on. I did not make a written solution to this despite writing the questions. I just kind of thought them through, checked things loosely. So you'll be seeing me actually solve these problems for the first time, but I'll try to be as informative as usual and give you good strategies in addition to actually solving the problems themselves while narrating my thoughts and solutions. So without further ado, let's jump into the first of those problems. So to begin with, I've started with a very basic question that focuses on all the different analysis techniques that we've had in this entire unit, or that you will have had in this entire unit. So I'm giving you a polynomial function, and I'm asking you to go through the entire vocabulary laundry list of things. So I'll go through one piece at a time, reminding you each time about what the definitions are and about what we're looking for in each case. So for the first one, our polynomial here is a negative noodle. So a good thing to get into your head, based on the fact that this is a negative cubic, is to just kind of imagine what the shape of that cubic looks like. That should be a negative noodle, so that gives you some nice guidance when it comes time to actually start differentiating and analyzing the function. May not be perfect, or there could be slides or something, but it's usually a good place to begin. So the first question asks us to find what we call the critical numbers of f of x. Critical numbers of f of x are the places where f prime of x is equal to 0, or where f prime of x is undefined. Assuming, of course, that f prime of x is undefined at a place where f of x is defined. So in any event, what's true is we must have that f of x must exist. I probably should use c for the critical numbers. In fact, I'm going to go ahead and change that. I'm not going to refilm it, but I will change it. So in each of these cases, we're going to say f prime of c equals 0, or f prime of c equals does not exist, but f of c for sure exists. So in this case, it's pretty simple. Take the derivative, set it equal to 0. So we need to compute the derivative of f of x. In this case, that's going to be negative 6x squared minus 6x plus 180. From here, I see that there's a lot of GCFing I can pull out. So I'm going to pull out a negative 6. That'll leave me with x squared plus x minus 30. And in this case, I can just factor whatever's there. We'll get x plus 6, x minus 5. And if we set that equal to 0, recognizing the fact that polynomials are always differentiable, so we're only going to get places where f prime of c equals 0. In this case, there won't be any does not exists, or the places where the derivative doesn't exist will not exist. In this case, we can see that there are, in fact, two critical numbers. Those two critical numbers are the values that make the derivative equal to 0. They are going to be x equals negative 6 and x equals 5. And I still haven't paid for my virus software. Now, what was I going to say? I feel like there was one more thing that I wanted to point out here. These are critical numbers. Oh yeah, the reason we look for critical numbers is because they're places where the function f could potentially have a relative maximum or minimum. They're all of the candidates that we might have for a relative extremum. Obviously then, when we talk about absolute extremum, it's a slightly different ballgame, but for here at least we should be knowing that we're finding all the relative possibilities. So there is A. Okay, for question B, it asks us what is the maximum value of f of x for 0 to x, or 0 to 6. Now in here they ask for the maximum value. Let's remind you first and foremost that the maximum value is literally talking about the y value itself, so we're looking for the y value. And then second, since we're given a closed interval, what you should be thinking to yourself anytime you're asked to find a maximum, or an absolute or global maximum, is the candidates test. We're going to find all candidates on the interval we're given, and then apply basically the extreme value theorem, which says that for a continuous function on a closed interval, there must be a maximum and there must be a minimum. So that's basically our strategy here. Now in order to use the candidates test, what that means is we need to find two things. We need to find the critical numbers, and we need to find the endpoints. Basically, those are our candidates to find a maximum value. And of course, in here, when it just says maximum value, that's just code for global or absolute maximum value. We're trying to find the highest y value that's ever attained by this function on here. And you might be tempted to picture our function from before and try to reason out where that space may be, but it's hard to say right now because we haven't placed it on an axis. So let's just go ahead and work our way through. So now we found out on the previous page that f prime of x equals 0 at two different x values, making a quick peek, it happens at x equals -6 and 5. So basically those are our two candidates first and foremost. Now the interval we're interested in though is from 0 to 6. That means that we're not actually interested in -6 as a candidate. It's just not running for the same election that we're talking about right here. The only candidate for us is x equals 5. So we're going to carry x equals 5 with, and then in addition, we'll grill the endpoints themselves. I'm a little bit hungry, so grilling it makes them sound kind of good. The endpoints themselves are 0 and 6, and we'll look to compare those y values as we look our way through. Sorry. So with the candidates test, anytime we're searching for global or absolute extremum, I'm going to make a quick little table. So we're going to compare our endpoints, which are 0 and 6, along with our critical number 5, and see what happens. And remember, we're plugging them into the function, because we're looking for the highest y value that actually occurs. And now naturally, I'll apologize right here that I did not give you nice values to plug in, but that's just life sometimes. So here we go. So let's start with the first one. If we plug in 0, f of 0 is going to be 7. And they say I don't give you anything. There's one really nice value. Our next one is going to be 5. So we want to figure out what is f of 5. And now obviously I'm not going to aim to give you this difficult arithmetic when you actually do this on the test, but for the moment we'll play along. We'll have -2 times 5 to the third, which is 125, minus 3 times 5 squared, plus 180 times 5, plus 7. So as far as values here, just kind of playing along, we're going to get -250 minus 75. Now on this next one, 180 times 5 is the same thing as half of 180 times 10, which is 1800 over 2, or 900, and then plus 7. So of course this couldn't be pretty, but we'll see what happens here. So minus 325, so let's see, 907 minus 325 is I think what our number is. And you know what, since we're here, good old-fashioned borrowing. It's one of the math lessons I remember from elementary school actually. So 2, when we subtract that, this is going to be 58. Looks like we get 582. Does that actually make sense? I think it's a good question. I guess I could borrow 10, 8. Yeah, 582. So our value is 582. That's quite a bit larger than 7. So 582 is our new kind of, front runner for the role of maximum value. And again, it would be 582 would be our maximum value. Fortunately, we need to check 6. Now, my thought here is by looking at this picture up here, I recognize that that relative maximum that occurs must be at x equals 5. So I'm expecting 6 to be lower. But of course, we need to check just to make sure. Like I wouldn't want to rely on my quick little doodle at the top to make sure. So if we plug in 6, we get -2 times 216 minus 3 times 36. It'll be helpful to know some multiplication facts. Plus 180, and I dropped the x there. Fortunately, I didn't screw it up there. 180 times 6, that's not going to be fun, plus 7. So down here, we're going to get -432. This will be minus 108. Happen to know the 3 times 36. Then this is going to be 180 times 3 is 540. This will be plus 1080. And then plus 7. So, what do we got? It looks like we have 1087 minus, let's see, if we subtract 8, that's going to be minus 440 minus 540. So we're going to do over here, let's see if we can do this right, 1080 minus 540 all over, 1087 minus 540 is going to be 547. So it looks like our value here is 547. And now we've got to compare all our values. As expected, we're looking for the biggest. So the largest of the values was at x equals 5. Our biggest y value was 582. That's how we could tell the biggest was at 5. And then to answer our question, the maximum value, the max value happened to be f of x equals 582. And again, that's the maximum value on this interval. Just in looking at a picture of the function, we can tell that over to the left it would have gone up even higher probably. But for the moment, we're focused on 582 itself. Okay, third question. On what interval is the graph of f of x strictly decreasing? And we're supposed to justify our answer. So if you recall, strictly decreasing is one of the two decreasing definitions. In this case, strictly means that we want less than 0 for f prime, meaning we want our slope to be non-zero and negative, like not just non-positive. So in this case, we're looking for where f prime x is less than 0. Well, fortunately for us, we already had calculated f prime of x. In fact, without going too far, we had f prime of x was equal to negative 6, x plus 6, x minus 5. And for the sake of making sure I'm correct here, let me check one more time. Yes, plus 6 minus 5. There we go. And of course, what we saw was that we had two critical numbers. Our two critical numbers that occurred happened to be at x equals negative 6 and 5. So with those critical numbers in place, we now want to check to see what's happening. Well, just from drawing a picture, I can see right here that the graph is going to be strictly decreasing on the left and on the right. So I could probably reason it out from there by labeling my critical points on the picture. But just to be safe, let's construct a sign chart, because of course that's kind of our purpose here, is to go over all the techniques that are there, particularly in my absence, since I'm stuck at home doing calculus stuff and standing for a couple hours before feeling pain all over. So from here, we'll go at f prime of x. So our two critical values were negative 6 and 5. Now there were no other additional important values but aren't critical, so just those two to look at. We want to see what's happening for x values less than negative 6. We want to see what's happening for values between negative 6 and 5. And then of course also for values bigger than 5. Now when I do this, I'm going to test out values. I'm going to plug in negative 10, I'm going to plug in 0, and I'm going to plug in 6. And we'll see what the sign looks like. So in here, we're plugging into our derivative f prime of x. So we're going to have negative 6 times negative, because negative 10 plus 6 is negative 4, so that's negative. And then negative 10 minus 5 is also negative. And a negative times a negative times a negative remains negative. So this is going to be a place where we are strictly decreasing, because the derivative is negative at that point. If we plug in 0, we get negative times positive times negative. Again, I'm just going negative 6 times positive 6 times negative 5. That gives us positive in the center, which matches what we saw in our little sketch up at the top. It does look like the function's increasing there. And last, when we put in 6, we get negative times positive, and the product of a negative and two positives is negative. Am I sure? Yes, I'm positive, unlike that interval where the derivative is negative. So given all that information, we were looking for the places where the derivative was strictly negative. In this case, that occurs on those two intervals. So if I were to conclude this out, I would say something along the lines of f is increasing. Oh shoot, that's a lie. I wasn't interested in increasing, I was interested in strictly increasing. F is strictly increasing. And then we can use interval notation or the notation that's there. I'm going to say it's strictly increasing for, I like intervals better, or inequalities better, x less than negative 6 and x greater than 5. And then to justify our answer, we can do that by setting the definition. We'd say because f prime of x is less than 0. And there is our explanation. Our complete analysis has been done. So again, pretty basic stuff. If we were doing strictly, oh, I wrote strictly increasing. I'm supposed to write strictly decreasing. You can see I am at my sharpest today. And by the way, there are 61 problems that I'm going to be doing here, so yay! But there we go. That is how we'd attempt strictly decreasing. By the way, if the word strictly was not here, let's say it just said decreasing, our only difference, in addition to getting rid of the strictly, would be that we would have less than or equal to negative 6 and greater than or equal to positive 5. That way we'd have everything covered in this case. So just something to note. It'll come up later on. Boom. Okay, the next one says find the x-coordinate of all the local minima of f of x. Justify your answer. Well, in this case, I'm not going to spend time recreating this entire process. There's lots of stuff to do. Ninja Warrior Championships are on tonight, and I want to see someone win. I hope it's Drew Dreshel, huge Drew Dreshel fan. Now, we want to figure out where the local minima happen to be. So looking at our sign chart will be an ideal strategy because it'll show us what's happening with the derivative. We can find the place where the derivative changes appropriately. Now for the moment, if we think about, and let's see, we can, let's think right up there. Thinking in our brains. Actually, this is a cloud in this case. If we think about what a minimum looks like, minimum, or minima, local minima especially, look like this. Our functions have to go down for a while before they begin to go up. And that point at the bottom where they stop going down and begin going up are what we call our relative minimum. What we're looking for then is we're looking for f to go from decreasing to increasing, or more relevant to us, we're looking for f prime to go from negative to positive. So looking over at our table, we're looking for the critical value where f prime changes from negative to positive. And looking over here, I happen to see it right in our table. Noticing the signs of the derivative, we have f prime is negative, 0, positive. Then over here we have positive, 0, negative. If we're looking for a minimum, that clearly occurs at x equals negative 6. So we could say, in fact I'll say it as properly as possible, f has a local minimum, and it has it at x equals negative 6. And our reason is because, and now we cite that specific sign change. It's because f prime, and we could say f prime of x, but make sure you don't say it. You do not need to pay Stephen King. It is because f prime changes. F prime doesn't change its close. F prime doesn't change its perspective. It's because f prime changes from negative to positive. And if you'll forgive me, I'll do it right. Changes from negative to positive. And there is our work. We've identified the fact that there's a local minimum there. Now again, I'll remind you, we knew there was going to be one there just from sketching a quick little negative noodle, Franklin terms. But this way we've formally proved it. And again, you might think of this, if you're looking for the name of this technique we used, we're using what's called the first derivative test. That's just the name for this pattern of sign change telling us what's there. Also now, just in case you're a person that's like, well, I don't want to use the first derivative test, and someone else is like, I second that motion. You could also instead look further and use the second derivative test. So if you wanted an alternate strategy, like we need to find our derivative really fast, our derivative would be negative 12x minus 6. Prime is negative 12x minus 6. So in this case, if we wanted to check whether or not we had a relative max or relative min at negative 6, we could plug in that value. In this case, that'd be negative 6. That would give us 72 minus 6, which is 66. Because the second derivative is positive there, that means that we are concave up at a critical number. And according to the second derivative test, that tells us that we have a relative minimum at x equals negative 6. So again, your choice, you could use the first or the second derivative test. Typically, my rule of thumb is if it's easy to compute the second derivative, especially with polynomials, you probably should just do that because it's the fastest way. But if we already have a table written, why go that way route? And please don't let me keep twisting around. So yeah, so second derivative test would have been a possibility as well, but not my recommendation. I endorse the first one because we'd already done all that work. So why do it twice? Especially when you have 61 problems to do if you're me. Okay, E. It asks us for what values of x is the graph of f of x concave up. Well, lucky for us, we've got a lot of different ways to talk about concave up, but the simplest definition is simply that the second derivative is positive. And fortunately for us, we just found out, or just computed, that f prime of x is equal to negative 12x minus 6. Now, if you're coming in out of nowhere, I would hope that you can still figure out what the second derivative is equal to without much trouble. So I'm just leave it at that. Now, in order to check concave up or concave down, we need to check for the places where f double prime changes signs, because that would be a place where the second derivative could be positive or negative. So in our case, I'm going to set this equal to 0. That's going to give me the equation negative 12x equals 6, which means that x equals negative 1/2. Now this, we will find pretty soon, is going to be our POI. Technically, at the moment, it's just a potential POI, but again, we're dealing with polynomials, so things are really well behaved. To make sure I've got everything set up here, I would then do a sign chart, but in this case, my sign chart would be with the second derivative, not the first derivative. So in my sign chart, since I'm using the second derivative, I'm going to break it up at the important value, or our potential point of inflection, where we know the second derivative is 0. Then we'll look and see what the sign of the second derivative is doing for values smaller than negative 1/2, as well as for when values are larger than negative 1/2. And again, just as we've done before, I'll pick a test value in each one. So seeing what we got here, if we plug in negative 100, that'll give us a huge positive number. It'd be literally positive 1200 minus 6. That's clearly positive. And on the other hand, if we plug in 0, we're going to get 0 minus 6, which is negative. So now we were interested in what was happening here with concave up. Concave up. So basically we were looking for the positive. So we would then say at this point that f is concave up Nope. For x values less than negative 1/2. And then our reason or our justification would be because of that sign. It'd be because f double prime of x is less than 0 there. And again, I might box the interval itself that solves our question, but there's our work. So we're talking concavity, we're talking about the second derivative, and then once more time, looking up at our original sketch, concave up would be on the left side, which is exactly what we found. So it looks like we're doing pretty well here so far. Okay, for f, it next says, and I have a feeling I'm going to regret this question horribly, but it's a good question nonetheless if I had spent more time making the numbers nice. It asks us to write the equation of the tangent line to f of x at its point of inflection. So we're talking about at the point of inflection. So drawing our quick little illustration here, our point of inflection is probably right about there, something like that. So I'm expecting a tangent line with positive slope, just based on my drawing, and then of course we'll have to find everything else. So in here, going to be kind of a mess. First and foremost though, to find the point of inflection, we said for this polynomial it's sufficient to check where the second derivative changes signs. More important for us though, since this is a polynomial, we just need to figure out where f double prime is equal to 0. Now we saw that f double prime of x was equal to, I want to say, was it negative 12x minus 6? And we saw that when you set that equal to 0, you get x equals negative 1/2. And that should actually work. So basically right there, there's our x value. That is x sub 1, that's where the point of inflection is occurring. Next we need to go on a lovely, fun journey, actual fun may vary, to figure out the slope and the y value at that point. Now because I know it's going to be miserable, and I've brought this on completely and totally myself, and probably no one will watch this because it's such a miserable question to compute, I'm going to start by figuring out what the y1 value is. So specifically I want to figure out y1, which is going to be f of negative 1/2. And I'm hoping this doesn't come out as bad as I might have accidentally done it. So we need to plug in negative 1/2 up there. So plugging in as we go, negative 1/2 to the third is negative 1/8, minus 3 times 1/4. This will be minus 90, because half of 180 is 90, and then a minus sign. And then plus 7, because, of course, plus 7. That was dumb of me. Okay, and here, we're going to get, it looks like 1/4, because that's positive 2/8, or 1/4, minus 3/4, and then minus 83. Thanks for that, me. So simplifying a little bit here, we're going to get minus 2/4, or minus 1/2, and then this will be the same thing as minus 166 over 2, which gets us a y value of minus 167 over 2. So that, my friends, is our y1 value. So it can't possibly be worse than that, but again, I apologize. That was just annoying, but I just didn't want to spend another half hour laying in bed trying to find a better function. Save those for the tests. So from here, the last thing we need is we need slope. Like, we don't know what the specific slope is. We expect it to be positive, but we don't know the slope itself. So to find m, we're going to do that by computing the derivative at negative 1/2. Now our derivative in this case, like, it'd be helpful to have that handy. Let's see if we can go pull it back up here. I'm going to go with the actual classic derivative here. Want to get the full thing. So there's our derivative in the already ready there. Oh, I put it on the wrong page, didn't I? That's what happens when you have a bunch of stuff to do. Okay, so there is our derivative. Again, we're just importing that from our work from before. Reward ourselves for good. Reward ourselves for good work. We'll have negative 6 times 1/4. Let's see, minus 6 times negative 1/2 is going to be plus 3. And then it looks like plus 180. So simplifying a little bit, that's going to be negative 3/2. Yeah, negative 3/2 plus 183. Simplifying a little bit, we're going to have negative 3/2 plus 366 over 2, which gets us to 363 over 2. So that is one steep little point of inflection slope. The important thing is, though, we just found our slope. There it is, which means we can wrap this puppy up. Let's see, it's going to be y minus 167 over 2 equals 363 over 2 times x minus a negative 1/2. So this should be our tangent line. And again, it's not very tan. In fact, I've written it in purple. But, oh my goodness, I hope that's correct. So at this point, I could go check on Desmos, and in fact, I think I will, just because we're here. Let's see if we did it right. Desmos. Of course, I can't see because I'm not wearing real glasses. Our function, f of x, is equal to negative 2x cubed minus 3x squared. Pray with me, friends. May this actually be done correctly so I don't have to feel guilty about it. Y plus 167 over 2 equals 363 over 2 times x plus 1 half. Now let's see. So now this picture looks terrible. Let's see what we got here. Can we tell anything? We cannot. So let's see if we can make this thing bigger. Okay, we know where those mins and maxes are. Let's go negative 10, 10. Okay, we got that. 300, 1,000. Okay, look at that. Okay, so the question is, did we get it? Heck yes. After all that work, it looks like we did it correctly. Good job, us. Well, to be fair, mostly me in this case, but you know, hopefully you got there too. But again, nothing that crunchy arithmetically on your actual exam. But we found it. Okay, before I pause and let this go to another video, let's do a couple more problems here. Let's hit number 2 for sure. So on number 2, it asks us to locate all points of inflection for each function and to justify our answers. So in here, there's lots of different strategies to take. The most important thing though to remember is if we're talking about a point of inflection, a POI occurs when f double prime changes signs. And I'm not writing where f double prime equals 0 because that's going to lead you astray, my friends, very much on some of these problems that we'll see in the next couple. So be warned, bad things could happen. So now before we attack g of x, I'm going to cosmetically alter it. I'm going to rewrite this as, or I'll imagine this as x to the 1/3 times x to the first minus 4. I'm going to distribute it in. I'll get x to the 4/3 minus x, minus 4 x to the 1/3. And we'll see if this pays off. Maybe it will, maybe it won't. So multiplying everything, or differentiating here, we'll try to find the derivative. Since points of inflection, those are helpful to start with. We'll have 4/3 x to the 1/3 minus 4/3 x to the negative 2/3. And then that was just the first derivative. So next I'm going to compute the second derivative. That's going to be 4/9 x to the negative 2/3 minus, and it'll become, plus. It'll be plus 8/9 x to the negative 5/3. So there is our second derivative. We want to figure out where it potentially changes signs. Now this could be somewhat challenging. I shouldn't reach to scratch my back. In here, what can we do? I'm going to pull out some GCFs just to see if that helps a little bit. The GCF is always the smallest power, by the way. So I'm going to rewrite this as 4/9 x to the negative 5/3. Now when you pull out negative 5/3, that's going to be like dividing by negative 5/3, or x to the minus 5/3 power. That's going to leave us with 1 x to the first power. We can make sure this works in just a second, by the way. And then that'll leave me with plus 2 afterwards. So looking at all these ingredients, or rewriting this expression a little bit better, we'll get 4 over 9 x to the 5/3. And by the way, if you distribute this, that's negative 5/3 plus 3/3 is negative 2/3. So I think we did the job. Good job, us. And then that'll be the outside, and then we'll have just x plus 2 on the inside. Now if we try to figure out where this is equal to 0 or where it's undefined, we'll see that there are 2 places here for us to consider. That's going to occur, and actually I'm going to move this up so that I don't run into my own face at the bottom. If I can't sit, I can't use the green screen. So in this case, that's going to occur at either x equals negative 2 or 0. So we have 2 potential candidates for our point of inflection. So let's go ahead and create a table and see what happens, especially because I'm not sure exactly what's happening with this function. So we'll do x. So g double prime, we said it was breaking up at negative 2, also at 0. We knew that the derivative was 0 there and undefined here, but that doesn't matter because on the original function it's completely defined, so we're okay to check. That could be a point of inflection. We're going to have to check values less than -2, values between -2 and 0, and values greater than 0. So as far as values to test here, I'm going to plug in 1, I'm going to plug in -1, I'm going to plug in -3, and we'll see what happens. This might be actually a bad choice. Actually, since we're plugging in power or things that will be cube rooted here, I'm going to put in -8. Just trust me on this one, it'll feel better. So as far as signs themselves, I'll start with 1 because 1's going to be the easiest. We'll have 4/9, and again what I'm plugging into is right here. Well, 4/9 times 3, that is positive. So that's a good start. Next we'll do the negative. So -1 to the 5/3 power is still negative. So we'll have -4/9 times +1, because -1 plus 2 is 1. That gives us a negative. And finally, if I do -8, like the important thing in here is that it's going to be a negative number in front, and it's going to be -6 on over here, which means it's going to be positive. Now in this case, that's kind of interesting. It looks like we actually have 2 points of inflection. So let's make sure that we draw that conclusion here. We have 2 POIs. In fact, I could say G has 2 POIs at x equals -2 and 0. And then for our reason, it would be because G double prime changes signs. And there's our work. And I feel pretty confident in this one. I feel like this is what happened, but there were some tricks here. I will say this is a little bit harder than it looks. I probably made a poor choice for our first point of inflection question on this review, but hey, that's what happens when you're stuck like I am under house arrest. So voila, there's A. Okay, B. B is a classic favorite, almost like the counterpoint to the first problem we just saw. So in this case, we want to again find the points of inflection, so we're looking for where H double prime will change signs. So in here to start things off, I'll go with a cosmetic look before anything else. This is x to -4 minus x to -5. Before though anything else, let me point out that x cannot equal 0 in this situation. The reason why is that if you plug in 0 to this guy, you don't get some harmless benign value like 0. You get 1 over 0 minus 1 over 0. And them things do not cancel out. What's happening is there's actually a vertical asymptote at x equals 0. So we need to make sure that 0 cannot be 0. Oh, come on, my computer. 0 is not a point of inflection. So let's make sure that we're aware of that first and foremost. After this, it's just a matter of differentiating a little bit. Get -4 x to the -5 plus 5 x to the -6. We'll do one more derivative. Be 20 x to the -6 minus 30 x to the -7th. Once again, I'm going to pull out a GCF. Well, let's do it this way. Maybe this will be a nice way to show it differently. This is 20 over x to the 6 minus 30 over x to the 7th. I'm going to get a GCF by multiplying up and down by x. When I do that, that gives me a 10 over x to the 7th I can pull out, and it leaves me with a 2x minus 3 factor. So now if we set this equal to 0 or undefined, to find potential points of inflection, we have two candidates, of course, x equals 0 and x equals 3/2. Now in this case though, we already mentioned 0 can't be a point of inflection, so your instinct should probably say it's 3/2, just to make sure, again, because I don't know which videos you guys are watching. We'll split this thing up. We'll go 0 and 3/2. Thankfully, with those values in place, we can actually spread this around a little bit. This is 0, this is clearly undefined, and this is not a POI, so we'll just keep reminding ourselves of that. Again, we're checking H double prime because we're talking about the second derivative and looking for points of inflection. So we'll go there. And then from here, let's see what else we got. We'll pick out some values to test. I'll choose 1, I'll choose 2, and I'll choose -1. So plugging in these values, I'm going to do it a little bit quickly. Again, where we're plugging it in is right here. If we plug in -1, we'll get -10 times -5 is positive. At 1, we'll get +10 over times -1, which is negative. And then at 2, we'll get +10 over 2 to the 7th, +10 over 128, who cares what that is? It's positive. And then this will be positive as well, which means this is positive. Now again, the instinct, you can kind of see what I'm trying to trick you with here. The instinct is to say there's points of inflection at 0 and 3/2, because at both of those x values, the second derivative changes signs. In our case, though, the only one that matters is the one that exists. We already said 0 cannot be a point of inflection. It's just not possible. So in here we can say that there's only a point of inflection for, we called it h of x, and it's at x equals 3/2. And we're supposed to justify our answer, which I really don't want to do right now, but that's okay. And our reason is because h double prime changes signs. And I'm going to just tack on there just as kind of a reminder, and h of 3/2 exists, because really that's the reason why 0 doesn't qualify, is 0 does not exist right there. And you know, I gotta say, as I'm doing these things, I'm actually doing a really good job of answering the questions and talking through them and thinking it through, but I'm not really enjoying it. So, I don't know. There's nothing you can do about that, but here we are. Okay, final question I'll do before taking a short little break here. It says the second derivative of function k of x is given by k double prime equals that thing. Find all points of inflection. So now the first thing I'm going to do is I'm going to thank myself for literally giving myself k double prime to work with, because that saves us a little bit of trouble. So in looking here, we're talking about points of inflection one more time, probably I think the last one for a while. K double prime can factor out into x squared quantity 3x minus 10. And in fact, if we set this equal to 0 to get potential values, with that continuous polynomial derivative, we have a polynomial, everything should be fine there. We have some candidates there of 0 and 10/3, which by the way is 3 and 1/3 for those of you who like the awkwardness that is mixed numbers. So from here, we have two different places to check. Now, oftentimes what will happen, and I'll tell you this because I've written this multiple choice question many, many times. I've written this multiple choice multiple times. Most of the time people just go, cool, 2 points of inflection, done. Unfortunately, that would be incorrect. There aren't actually 2 points of inflection here. And the reason has to do with that requirement that the second derivatives change signs. So let's just investigate for a moment. Let's just play it safe. Let's be uber cautious. And let's see what happens. So again, we're looking for values greater than 10/3, values between 0 and 10/3, and values less than 0. And as usual, I'm going to choose simple values, -1, 1, and let's go 42, because who cares? So as far as our other values in here, I should have marked them first. We know both of these produce 0 in our second derivative. So if we plug in -1 up in here into our second derivative, we're going to have positive times negative is negative. If we plug in +1, we're going to have positive times negative is negative. And then finally, if we plug in 42, we're going to have positive times positive is definitely positive. Yes, I'm sure I'm positive. Now over here, what we found is there's definitely a point of inflection at 10/3, because our sign changes from negative to positive. Unfortunately, though, there's not a sign change at x equals 0. It just goes from negative to, well, it's still negative. Nothing changed. Still having a bad day. Second derivative, not feeling it right now. What that creates is I oftentimes call this a Super Bowl, which probably owes me money to the NFL, but I call it a Super Bowl because what happens is it's just extremely, sorry, it should be concave down. It's just extremely flat at that point, and it just happens that it's so flattened down there that it still produces negative second derivative on both sides of the thing, even though it zeroes out for a moment. So in this case, the only point of inflection, only at, we'll say it's at only at x equals 10/3, and our reason is because k double prime changes signs. And I am definitely not getting a tattoo of k double prime changes signs anytime soon, because I'm sick of writing blah 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 double prime changes signs. But there it is, there's your stuff, and consider this your warning. I could ask this question. Hint, I'll probably ask this question. Okay, this next brings us to question number 4. Question number 4 is one that I feel like when I wrote it, I really enjoyed writing it. I think this is a great question. I think it really probes your understanding of all these concepts in a way that the first problem probably doesn't. That one's more focused on the basic rote skill. This is focused on, can you actually do this stuff? And making things challenging here and making it interesting for me is the fact that we're looking at a piecewise function. So by having that piecewise function, there's all sorts of interesting behaviors that happen. So first and foremost here, the first thing we have to look at are the critical numbers of p of x. So a good place to begin, of course, anytime we look for critical numbers, is to think about when does p prime of x equal 0, or where is it undefined. So to start things off, I'm going to compute p prime of x, and then we'll have to do a little investigation to find some of the other stuff. So with piecewise functions, we just differentiate each part. That'll give us 2x plus 6 up there. When x is less than 1, it looks like negative 4x when x is greater than 1, or greater than or equal to 1. Now with each of these pieces, we need to consider, of course, the domain restrictions, like only certain behaviors are occurring in certain places. In addition, we need to make sure that our function is even continuous at the boundary, because if it wasn't, bad things would happen. So first thing that I can look at to check if it's continuous at 1 is I could just look at the limit as x approaches 1 from the left side of p of x, and compare that to the limit as x approaches 1 from the right of p of x. Now again, this isn't something you normally have to do, but because it's a piecewise function, this is where things really pop up. So from the left side, we get 1 plus 6 is 7. From the right side, we get 9 minus 2 is 7. So that tells me that we are nice and continuous at x equals 7. So that brings me down to our next part. So looking at p prime of x, we've got a couple possibilities here. First possibility is that the top branch equals 0. That's going to occur at x equals negative 3. Because of course what I'm solving, sorry, went too fast, is 2x plus 6 equals 0, and that occurs when x equals negative 3. So now, important for us to note, negative 3 is less than 1, which means this is in fact a critical number. So over here, if we're looking at our critical numbers, like we've found one, we have in our inventory x equals negative 3. Okay, our second thing to check. We need to check the second branch and figure out if it's equal to 0 there. So the question is, when does negative 4x equal 0? Clearly that occurs when x equals 0. But on this branch, we're talking about values that are greater than or equal to 1, which means there is not actually going to be a critical number at 0. Basically, that potential max or min occurs outside the domain that that part of the function is behaving on. So we do not get a second critical number from that. Where we could get a critical number, though, very important to note, is we could get a critical number at the boundary, because it's possible that there is a sharp turn or some non-differentiable point there. So to check that, if you'll recall, we look to see if the derivatives limit exists at that point. Because basically what we're checking is the derivative continuous at x equals 1? So we're going to ask ourselves this question by plugging in and seeing. We'll have 2 times 1 plus 6. We'll compare that to negative 4 times 1. So our question is, does 8 equal negative 4? The answer is, of course it doesn't. What that tells us is because our function was continuous at x equals 1, but its derivative is not, that tells us that we have a sharp turn at x equals 1. And for our sake, what that means is we found a value where p prime is undefined. That means that we have a second critical number at x equals 1. So there are actually 2 critical numbers for this function. And again, getting in there, challenging. Like, this is kind of a plus question, but again, I think this is all work that you should be able to do. So take it for what it is. Great question, there it is. Will I put this on a test? We'll see. Okay, the next question. For what values in the graph of p is the graph of p increasing? Justify your answers. Well, here's stuff that we have. We just found these critical numbers. And it's critical we don't waste our time finding them again. So if we're looking for increasing or decreasing, we're going to look at the critical numbers and then compare what's happening with the derivative around them. So for our sake, what I'm going to do is I'm going to set up a quick sign chart. I'm going to compare values of x to values of p prime. And of course I can't draw a straight line to save my life. It's okay. Hopefully saving my life requires something better. We had 2 critical numbers at negative 3 and 1. We knew one of these at 1, the derivative was undefined, and at the other, our derivative was 0. And then just because we're probably going to need it, let's grab our derivative also. Oh, come on, really? 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 Okay, whatever. I'm just being whiny at this point because I'm not feeling great. Okay, so there's our derivative. Also imported from the previous problem. So let's see what happens when we plug in our stuff to this derivative. So we're looking first, actually, I'll write this in the purple color. Looking for values less than negative 3, values between negative 3 and 1, and values greater than 1. So first and foremost, if we plug in values less than negative 3, they'll be using stuff like negative 4. That's going to occur when x is less than 1. So that's going to mean that our derivative will be negative 2 minus 4 plus 6. It's negative 8 plus 6, which is negative. So we are decreasing for values less than there. By the way, I'll also note this is increasing, not strictly increasing, but we'll play with that in just a moment. Second thing, if we're choosing values between negative 3 and 1, those are all going to be values less than 1 also. So in this case, if I pick a value like negative 2, we'll have 2 times negative 2 plus 6, plugging it into the correct place, which is going to be 2. It is 2, but more importantly, 2 is positive. Finally, for the last one, if we choose values greater than 1, a value like 10, then that's going to be negative 4 times 10, which is negative. So in this case, what we've just seen is we've seen what the signs are for each of these parts of the functions. So we were looking for the place where p of x is increasing. So that means we want to know where p of x is greater than or equal to 0 at this point. And again, it's or equal to because it's not strictly increasing, just increasing. So the only place where that happens is right around here. So in looking at this, we'll have to say that p is increasing for, now in our interval we got to be careful. It's going to be specifically for 3 less than or equal to x less than 1. Now the reason I'm not including 1 is because, of course, we already said x is x equals 1 is a critical number, but more importantly, it's a sharp turn, which means the derivative doesn't exist there. So we don't include that in our increasing part. It's just nothing. It's just nothing's happening there. So p is increasing for that interval, and then our reason would be because p prime of x is greater than or equal to 0 there. So really, probably the best increasing function I could get. And again, if you're able to do this function, I think you understand the concept of increasing. Muy bien. Okay, next we're supposed to find the value of the mean value, or the value guaranteed by the mean value theorem for p of x on negative 4 to 1. Now, something to note here before we even start is that it says that there's a sharp turn at 1, or we've already established that there's a sharp turn at 1, so you might be tempted to say that the mean value theorem can't be applied. But remember, in the mean value theorem, you only have to be differentiable on the open interval. It doesn't matter what's happening on the endpoints. And although that rarely comes up, in this case it does. You would need to be continuous on the closed interval, but that's obviously established. We already showed this is a continuous function, so we're actually okay to do this. So the mean value theorem for p of x on negative 4 to 1. What I'll note for here is that we're describing all of the values up in that top branch. Basically, p prime of x is equal to x, or 2x plus 6 for all the values less than or equal to 1, or less than 1. So basically, let's focus our attention there. But let's play for the moment. So first and foremost, if we want this to be true, we need to figure out where p of 1 minus p of negative 4 all over 1 minus a negative 4 is equal to p prime of x. And specifically, it's going to be on negative 4 to 1. So that's what we're looking for. So in here, as far as plugging in values, p of 1, we already established that's 9 minus 2 times 1 squared, which is 7. P of negative 4, that's going to be 16 minus 24. We'll deal with that in a moment. All over 1 plus 4. 7 minus a negative 8 is 15. Oh, cool. 15, 7 minus a negative 8, that's correct. It's 15 over 5, which is 3. We want to figure out where 3 equals p prime of x. And again, I'll just emphasize one more time. We want to figure out where p prime equals x on negative 4 to 1. So now we've already established before that p prime of x, and I'll just rewrite it because I'm not going to go back. P prime of x is 2x plus 6 when x is less than 1, and it's negative 4x when x is greater than 1. I'm even going to drop the or equal to because of the fact that it's not differentiable there. So with those pieces in place, though, what we said was since this interval is clearly, I'll do it this way, since this interval is clearly less than 1, we're describing the first half of the first branch, we can basically ask ourselves, when does 3 equal 2x plus 6? And again, we should get a value on this interval, otherwise we've broken the mean value theorem, and that would be mean value theorem. So plugging in all these pieces and solving this amounts to a simple algebra 1 problem. Negative 3 equals 2x, and that means x equals negative 3 halves. So there is our one value. Is it between negative 4 and 1? Heck yes it is. We have done our job. Good job, us. And again, by the way, if you were working your way through here, I believe, let me see if I can do this right. Would there be another place? There's not. That's the only place that works. So we're done. Ignore me. Okay, fourth question. Are there enough? Can I finish this? I think I can. Find the x values guaranteed by the extreme value theorem for the function p on the interval of 0 to 3. Basically, the extreme value theorem says continuous closed interval. What that gives you is a max and a min. So in order to talk about the extreme value theorem, we need to guarantee that we have continuity and talk about things on a closed interval. Fortunately for us, we have a closed interval, and we already established in the first part of this problem that this function is continuous. So basically, there are values guaranteed by it. Now, as far as the question at hand, where it says find the x values guaranteed by the EVT, what that means is we want to find the x values for the extrema, for the absolute max and absolute min. So in other words, we're going to need to use the good old-fashioned candidates test. And again, it doesn't have to be super difficult, but we'll be super careful as we do this. So we're looking at the candidates test. These are all our possibilities here. Important to remember are some things. We said, in fact, I'll just steal all this stuff along. Boom, boom, boom. Let's make this smaller. Boom. Okay, so we're going to do the candidates test here. So as far as things that we have our critical numbers are -3 and 1. As far as our candidates test in this particular case, we don't need to worry about -3 because it's not between 0 and 3. We do need to check at x equals 1, and otherwise we need our endpoints. So the candidates that we have in this case are x equals 0, 3, the endpoints, and 1, the critical number. So making a quick table, of course we've got p of x as our function here. We're going to look at the endpoints and our critical value. So first of all, if we plug in 1, we've done that a few times, we're going to use this first branch. We're going to get 9 minus 2 times 1 squared, which is 9 minus 2, or 7. So there's a candidate. That could be our highest y value, it could be our smallest. We're going to see if it is. Next, we're going to look at x equals 0. So I'll change colors as we go through here. If we do x equals 0, that's going to occur in the branch where x is less than 1. That'll be 0 squared plus 6 times 0, which is 0. Finally, we're going to look at 3, and since 3 is bigger than 1, we're going to plug it into the second one. We'll have 9 minus 2 times 3 squared. That's 9. 9 minus 18, which is -9. So basically we have 3 places. We're supposed to find the x values for the minus, smallest, and the biggest ones that are there. Looking at our ingredients, I see the biggest is x equals 1, and I see the smallest is x equals 3. So the 2 values that were guaranteed were x equals 1, which is our maximum, and x equals 3, which is our minimum. So those are the 2 x values that satisfy the extreme value theorem because they correspond to the absolute extrema of our interval. So tough question to phrase out, maybe not my favorite way of asking it, but definitely something you should be capable of. More than anything else, you should know what the extreme value theorem is and recognize that when you're talking about maxes and mins, you need the candidates test if you're on a closed interval. Okay, third, we want to find all the relative extrema of p of x. Helping us along the way is our calculations from before that included the derivative and the critical numbers. So what's important here to note is that if we're talking about relative extrema, they will occur at critical numbers. There's actually a theorem, I believe that was in your notes, that says the only time relative extrema are there are at critical numbers. They can only occur at critical numbers. It's critical you remember that. So basically the only places we need to check are -3 and 1. Now to help us with this though, we've already done some work that supports us here. We already created this sign chart. And I am all about not doing the work multiple times. If you're confused about it, go back to that question and do it there. So from here, boom, 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 we're looking for relative extrema. So in looking at our picture here and looking at the sign behavior, I see negative slope, 0, and then positive slope. And then I see positive slope, undefined, and negative slope. So basically looking at these ingredients, what I can see is that it looks like we have I'll use local instead. Looks like we have a local min at x equals -3. And our reason would be because p prime of x changes. And we'll say from minus to plus. And again, I'm not writing this as formally as I would. That's what happens when you have to do 61 problems and it takes forever. Okay, our second one, we can say that there's a local max as opposed to Dmax that sits by Alvin's. There's a local max at x equals 1, and our reason would be because p prime of x changes, and in this case it changes from positive to negative. Boom. So again, by having all that work, by investing ourselves in the critical numbers from before, this makes this problem go a lot faster. So there's 4e. Again, if you have questions about it, you can always refer back to, looks like 4b would be a good choice. Okay, and the last part that we'll look at here, we've got our question 4f. It says find any points of inflection of p of x. Well, again, I'm going to be that guy. We already, oh, that's not the work that I wanted. Let's go steal our derivative and critical numbers. Technically, I probably only need the derivative. So again, hopefully when you hear points of inflection, your mind immediately starts to think about the second derivative. So that's exactly what we're going to do here as well. If we have our first derivative as p prime of x, then what we need to find is we need to find our second derivative. So we're going to compute first p double prime. So looking up here, we're going to have the derivative p prime is 2 when x, or sorry, the second derivative is 2 when x is less than 1, and the first derivative is negative 4 when x is greater than or equal to 1. So now this is an interesting second derivative. This is pretty funky actually. But for the moment, we want to check if there are points of inflection. So if you're not sure, let's make a quick sign chart. And it does not say justify your answer, but I probably will anyway. So in p double prime, we've got a critical number, and they're an important place to check at x equals 1. It's our only boundary. Notice there's no other place where these things are equal to 0. They just don't happen anywhere. So we're going to use 1. We know that it's undefined at 1. There's issues happening there because of the sharp turn. So we'll have x less than 1 and x greater than 1 to consider. Choosing some test values, I'll choose negative 2 and I'll choose 42.42. So looking at our second derivative, it's pretty easy to calculate. The second derivative when x is less than 1 is just always positive 2. So in other words, the second derivative is positive. And for values larger than 1, the second derivative is always negative 4, which means it is always negative. Now in looking at this, we established earlier that the function p is defined at x equals 1. So p is continuous at x equals 1. So that means that we're okay to talk about points of inflection there. There could be one there. In this case, what we see is p double prime changes from positive to negative there. So we could say, in fact, at this point, that p has a POI at x equals 1. And our reason would be because p double prime changes signs. Now at this point, we've done all this work on number 4 and we've never looked at the graph itself. Well, I feel like I should change that just because this was a mess of a problem. So forgive me for being curious about the monstrosity that I created. And we'll see if this all adds up. Otherwise, I'm going to be very sad here because my leg hurts from standing here this way. Why do you hate me? Why do you hate me, computer? X greater than or equal, because I can't see. And that's going to occur when 9 minus 2x squared. Okay, so here's our function. Let's zoom in a little bit. So there's our guy. The question is, does this guy look like what we described? Well, first of all, looking at this picture, I definitely see that the function is concave up on the left, and then it looks to me like the function is concave down on the right side. It's a little hard to see, but it looks to me like the second derivative is in fact negative over there. Now what's interesting here is we could in fact call this function p of x and actually ask Desmos to calculate some stuff for us, like for instance p double prime of x, and notice it is in fact exactly what we expected it to be. It's exactly the second derivative we thought, so it looks like that does happen there. We have a relative maximum at 1, 7, have a relative minimum down there at negative 3, negative 9, not that it ever came up. I think we did a pretty darn bang-up job on this problem. So to celebrate our glorious victory, I shall do this and paste it into the last part of the problem as a token of our great work. Now with that said, I'm probably going to stop for today because I am exhausted and tired of doing this. And I can't bend. I have 16 out of 61 problems done, so I have about a quarter done. Oh well. Hope this is worth it and it's helpful to you.